Since so many things within our body and within human physiology are based on chemical gradients, let's talk a little bit more about it. Specifically, what's known as equilibrium potentials. Now, an equilibrium potential is the point at which an ion is no longer going to move down its chemical gradient. In review, we've talked about cells having a negative charge on the inside and a positive charge on the outside. Certainly the whole body is electrically neutral, but immediately on the interior of a cell, it's somewhat negative. Let's say more negative than the outside of the cell. That's why we represent this with a negative on the inside, positive on the outside. Negative 70 millivolts is roughly the resting state of most cells. At least most excitable cells, those that are selectively permeable to ions, that are capable of changing the voltage or differential in charge between the inside of the cell and the outside of the cell. So negative 70 to negative 90 millivolts represents the resting state. And once again, we have a much higher concentration of sodium outside the cell than sodium inside the cell. And the converse is true for potassium, where we have a super high concentration of potassium inside the cell and a much lower concentration of potassium outside the cell. These concentrations, otherwise known as chemical gradients, will allow for the diffusion of sodium into the cell and potassium out of the cell. And recall that sodium is moving down an electrochemical gradient because the positive charge on sodium is attracted to the negative charge on the interior of the cell, whereas potassium only has a chemical gradient favoring it to leave. Based on electrical charge or electrical attraction, potassium would actually prefer to stay in the cell because potassium is positive and the interior of the cell is negative. But because potassium's chemical gradient is so large, it disregards, or up to a point, it disregards the fact that it would prefer to be around the negative charge. And that's where the concept of an equilibrium potential comes in. An equilibrium potential is a charge at which these ions cease to move down their chemical gradients because they are deterred by the charge. Another way to look at it, or probably a more official, correct definition, would be where the electrical gradient is in total opposition to the chemical gradient. That is to say, in opposite directions. So let's take a look at this. If we look at sodium, sodium's equilibrium potential is positive 60 millivolts, as we see right here. And what I'm trying to establish or show or represent in this cell, very large positive charge to represent this cell being super positive, small negative charge on the inside of this cell. This cell has depolarized. Now, I will be honest with you, the term depolarization, or to depolarize, in my opinion, is somewhat of a misnomer, or not totally accurate, because when the interior of the cell becomes positive during a depolarization event, the exterior is actually becoming less positive or a little bit negative. So what has happened is the polarized state has just reversed. Now negative on the outside, positive on the inside, whereas on a resting cell it was positive on the outside, negative on the inside. Nonetheless, we're still going to refer to this as a depolarized cell because that's common nomenclature within human physiology. So the interior of the cell turns positive. It is turned positive because sodium was coming into the cell, sodium was coming in, sodium was coming in. Sodium continued to come into the cell. Now, certainly, other factors can cause cells to depolarize. We talked about pancreatic beta cells, where the retention of potassium in a cell helps facilitate depolarization, certainly not on its own, because sodium helps out in that process as well. That is to say, the influx of sodium. Influx of calcium could certainly also depolarize the cell. So I'm just giving one example of sodium, but sodium moving into the cell will depolarize the cell, making the cell positive in the interior rather than negative, like a negative 70 millivolts that we see here, we see a positive 60 millivolts right here. Positive 60 is sodium's equilibrium potential, which we write like this. E is referring to equilibrium potential, sodium, and 60 millivolts. 60 millivolts is the point at which sodium is no longer going to enter the cell. And more specifically, sodium is no longer going to enter the cell even though a couple things still exist. One, sodium still has a very large chemical gradient. That is to say, based on its chemical gradient, it would still love to move into the cell. To be very clear, for a cell to depolarize, to change voltage by sodium coming in, or any other ion for that matter that can depolarize the cell, not much sodium needs to move into the cell. As a matter of fact, very little sodium needs to come in to depolarize the cell. Point being is that there's still a bunch of sodium out here. But once the cell becomes so positive, and that so positive is positive 60 millivolts, once the cell hits positive 60 millivolts, sodium decides, I'm not going to move into that cell anymore. I have no desire to be around that large positive charge in the cell because sodium is positive and the interior of the cell now is super positive. This is even the other condition that I failed to mention, that there are still plenty of channels open for sodium to move into the cell. That is to say, the cell still remains selectively permeable to sodium either via sodium leakage channels or sodium gated channels. So once again, at positive 60 millivolts, which is sodium's equilibrium potential, sodium is going to decide, I'm not entering that cell anymore. It's too gosh darn positive. That is sodium's equilibrium potential. And we can see that over here on this graph. I realize on this graph this says negative 90, resting state is negative 70 here. Once again, that is not a huge deal. But I have it negative 90 here for a specific reason, and I will talk about that momentarily. But resting state right here, negative 90, could be negative 70. The cell depolarizes due to sodium influx. And let's just assume in this scenario that this is due to sodium leakage channels. Once again, a sodium leakage channel is always open. It's not going to close. So sodium can come in as long as it wants, and it will, until that cell reaches positive 60 millivolts. And once it reaches positive 60, sodium's done. Sodium is not moving in anymore because it would actually rather be around the negative charge on the exterior of the cell. Positive 60 is sodium's equilibrium potential. Negative 90 is potassium's equilibrium potential. And that's why I have negative 90 on this graph. So once again, potassium prefers to leave cells because there's a much higher concentration of potassium inside of cells than outside of cells. As potassium leaves, continues to leave, that's positive charge leaving the cell. So there are two reasons that proceeds to make the cell more negative or return to its resting state. One, because positive charge is leaving the cell, and two, because there's still those protein anions and negatively charged phosphate ions in the cell to help make the cell negative. Our focus now is just what potassium is doing. And as positive charge leaves the cell, which is potassium in this case, as positive charge leaves the cell and continues to leave the cell, it becomes more negative. As the cell starts losing positive charge, it starts becoming negative. So in this graph right here, which is a graph of a depolarization and repolarization event, this is showing the depolarization and repolarization event, depolarization and repolarization going back down to its relative resting state. And I say relative because I have this at negative 90. And we're also assuming that potassium leakage channels are open. So it's going to allow potassium to leave all day long as potassium wants to leave. And the point at which potassium no longer wants to leave is when the interior of the cell is so negative. We have these huge negative charges in here, small positive on the outside. It's so negative in here, potassium decides that it would much rather stay in the cell. Now, as I'm talking about this, we should not give ions or molecules any ability to think or have intent, and I realize that's how I'm talking, but please keep in mind I am just anthropomorphizing this whole process. Hopefully it's more understandable that way. Potassium, when it becomes super negative in the cell, even though it still has the huge chemical gradient, is going to stay in the cell because potassium's positive charge is attracted to the negative charge, the super negative charge, at -90 of the interior of the cell. So once again, this stops depolarizing here because the cell has reached +60. That is sodium's equilibrium potential, and potassium's equilibrium potential is -90 millivolts. And that's why this stops right here. I want to point out that this graph is a theoretical graph. I'm not saying this graph actually ever exists, or let me rephrase that the electrical activity in a cell actually is displayed by a graph like this. And I will fine tune these graphs as we move forward with neurons, which are nerve cells. But to be clear, sodium and potassium will move down their chemical gradients up to a point, and that point is their equilibrium potential. +60 for sodium, -90 for potassium. I made a brief mention of neurons. Neurons are nerve cells that make up the brain and the peripheral nervous system, which is essentially our nerves, some cell bodies, and collections of nervous tissue like the adrenal medulla make up the peripheral nervous system. I'll go into more detail on the makeup of the nervous system, both the central nervous system, i.e. the brain and spinal cord, and the peripheral nervous system. But the main excitable cell, the functional unit of the nervous system, is the neuron. A neuron and a nerve cell is the exact same thing. And this is what a neuron looks like. I use the word action potential. Action potential with regards to a neuron is the depolarization and repolarization event that happens along the axon to the axon terminals. So let's just talk a little bit about neural anatomy, that is to say the morphology of a nerve cell. This big circle right here, and I guess I should stop and say this should be a great example that not all cells are circular like I draw them. And this is really just one depiction of a nerve cell. Nerve cells are highly variable in their morphology as well. But most nerve cells have a cell body that we see right here that contains the nucleus and most of the organelles. They have dendrites, and the purpose of dendrites is nothing more than to increase surface area. So in that sense, they are very similar to microvilli. If these dendrites weren't here, the surface area of the cell body would be limited to just this circle right here. But by having these undulations, which are what the dendrites are creating, it's creating much more surface area. And the more surface area a cell has, the more ability it has to engage in metabolic activity, having specific receptors in channels needed to carry out any number of events. So we have dendrites that are coming off the cell body. On the other side of the cell body, we have what's known as an axon. The axon is this long structure right here. Coming off the axons, we have the axon terminals. The axon terminals contain synaptic vesicles that are essentially secretory vesicles. Because we're in a neuron, we refer to them as synaptic vesicles. Contained within the synaptic vesicles are neurotransmitters. So neurotransmitters are things like dopamine, serotonin, acetylcholine, norepinephrine, to name a few. And we'll talk about neurotransmitters in detail as we move forward in our discussion of the nervous system. So once again, dendrites, cell body. The cell body is also referred to as the soma. The axon coming off the cell body, axon terminals that contain the synaptic vesicles within which we find neurotransmitters. Now, one more morphological structure I need to point out is the point at which the axon departs the cell body. The point at which the axon departs the cell body is known as the axon hillock. And in and of itself, it doesn't look that exciting, but it's important for a very physiological event, and that event is threshold. In a subsequent video, I will talk about in much more detail the electrical activity that happens along a neuron. But in short, we have a depolarization event that spreads across the cell body. I should say it spreads across the dendrites and the cell body. The depolarization event that spreads across the dendrite and cell body is referred to as a graded potential, very, very similar to an action potential, but certainly some distinct differences. So we have the graded potential along the cell body, which depolarizes the cell. And then we have an action potential down the axon into the axon terminals, which ultimately is going to facilitate the release of neurotransmitters. And just like in pancreatic beta cells, where the depolarization event opened up voltage-gated calcium channels, the same thing is going to happen down here. We're going to get calcium-induced exocytosis of the neurotransmitters from the neuron. And once again, we'll talk about that in more detail. But here's the big take-home message. Threshold needs to be met at the axon hillock. That is to say, there needs to be a voltage that is met at the axon hillock for the depolarization event to continue down the axon. So we have a depolarization that spreads across the cell body. As long as that depolarization is at negative 55 millivolts, at the axon hillock, we will get the depolarization event all the way down the axon. So we get depolarization across the cell body, known as the graded potential. And as long as the voltage is negative 55 or more at the axon hillock, we're going to get a depolarization event all the way down the axon, spreading to these axon terminals, to all of these, that's going to result in calcium-induced exocytosis of neurotransmitters from the secretory vesicles. And in our next video, we will talk about in great detail what's happening within the neuron. Now, to be clear, what are these neurotransmitters doing? They are stimulating a downstream cell. So what I have right here in this image, I have one neuron. This neuron is drawn more simply than this neuron, but please understand that this neuron is engaging in the same activity as this neuron. This neuron is releasing a neurotransmitter. Let's say in this case, it's going to be acetylcholine. So there would have been a depolarization event that spreads along this axon, along the cell body, and then along the axon because it has reached threshold at negative 55 millivolts. Calcium-induced exocytosis releases the neurotransmitter, in this case, acetylcholine. Then that acetylcholine is going to then stimulate the heart, and most specifically stimulate the myocardial cells. That is to say, the muscle cells of the heart. And acetylcholine is actually going to slow down heart rate. And we'll talk about that in much greater detail when we get to the cardiovascular system. Now, if this were norepinephrine, it would actually speed up the heart rate. But my main point here is that there's a very, 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 very small distance in the realm of nanometers that the neurotransmitter travels from the axon terminal to the heart cells, either to speed it up or slow it down. And this is not limited to heart cells. Acetylcholine binds to skeletal muscle, the muscles, say, of our skeleton, our biceps, our quads, our hamstrings, what have you. And acetylcholine binding to skeletal muscle will cause the skeletal muscle to depolarize and then contract. And this is another image we can visualize to understand what neurons are doing and what neurotransmitters are doing. That is to say, there can be a whole series of neurons stimulating each other. So if we go back here, one may have been asking as you're watching and listening to this, well, what causes this initial depolarization in the cell body? Well, if this neuron is this neuron right here, it is these neurotransmitters that are going to bind to receptors to open up ion channels, specifically sodium ion channels, to cause this neuron to depolarize. And that depolarization event facilitates the release of neurotransmitters from this neuron to cause this neuron to depolarize. Now, to be certain, there is another neuron in front of this. The release of these neurotransmitters are stimulating this neuron. So this begs the question, what causes this neuron to depolarize? Because we don't have a neuron upstream of it. And that's a great question. It could be any number of things. It could be an aroma that maybe reminds you of your grandmother who wore that specific perfume. And so when you're smelling that, that's activating neurons to tell your brain, I'm smelling a specific perfume, which then may be activating other neurons that are eliciting memories specifically of your grandmother. So there's a whole series of events that happen with neurons, and we will talk about neurons in great detail. I want to take the opportunity to look at the electrical activity down the axon of a neuron. And this is what a lot of the graphs for action potentials look like, specific to the axons of neurons, the axons and the axon terminals. Like a lot of things in the body, this is highly variable, but this is one realistic depiction of what the electrical activity is going to look like. We are going to have the resting membrane potential displayed here in purple. This pink slanted line right here, gradual depolarization event from -70 to -55. -55 is threshold, which is the voltage at which is the voltage that must be achieved at the axon hillock to have that depolarization event down the axon. Now, I should back up and say on this graph, on the x-axis we have time, on the y-axis we have millivolts, -90 millivolts, -70, -55, 0, and +30. I realize that's not really to scale, but this will work for our purposes. So resting state at -70 millivolts. Right here, we have graded potential that takes the neuron up to -55 millivolts, which is threshold. And since threshold has been met, we have this big spike or depolarization event due to sodium influx into the cell. Now, we can see we're at +30 right here. That is to say, the cell is not reaching sodium's equilibrium potential, and that's merely because the cell no longer is permeable to sodium. And the reason it's not permeable to sodium anymore is because the sodium gates have closed. So the significance of threshold in this case at the axon hillock is that this is going to start opening voltage-gated sodium channels along the axon. And those voltage-gated sodium channels are going to open up very quickly and then close. But in that very small period of time, within that very small window of those voltage-gated sodium channels being open, if they open like this and then close, enough sodium is going to come in to allow that cell to depolarize up to +30. But it's not proceeding past or upwards of +30 because the gates have closed. Sodium is not given the opportunity to reach its equilibrium potential. To be clear, sodium's equilibrium potential is +60, and if the gates remained open, this would stop at +60 like we showed in that theoretical graph previously. But in this case, the sodium gates have already closed. At +30, sodium is no longer moving into the cell. At +30 is when the cell starts to repolarize. Now, one thing I want to point out is potassium is the reason the cell starts to depolarize. And potassium starts leaving the cell via voltage-gated potassium channels. To be clear, sodium was coming in via voltage-gated sodium channels. A common understanding or a common thought within physiology of neurons and the action potential of neurons is that potassium starts leaving the cell when voltage-gated potassium channels open, and that's totally accurate. But they are not opening right here at positive 30. They are almost certainly opening right here at threshold. That is to say, both sodium voltage-gated channels and potassium voltage-gated channels are opening at the exact same time. But the big difference is the sodium channels open much more swiftly and the potassium channels open very slowly. So the way I like to describe that is this. These are sodium-gated channels, voltage-gated sodium channels, and these are voltage-gated potassium channels. A voltage-gated sodium channel does that. It opens very quickly and closes. And I will show that it's even faster than that. So I'm going to take the potassium channel away. The voltage-gated sodium channel opens and closes just like that. Did you see that? It is so fast you may not have even have seen that. So the voltage-gated sodium channels open up very swiftly and then close at the same rate. But enough sodium is coming in to depolarize that cell up to positive 30 millivolts. Now, if we look at the potassium channels open up much more slowly. Potassium's leaving, but it's not leaving as quickly or readily as sodium because this channel is not even fully open yet until it reaches positive 30. So if I were to show both these at the same time, which is really hard, at negative 55 or threshold, the channels do this. That sodium channel open and close and the potassium channel is slowly opening. So they start opening at the same time. Potassium channels take much longer to open, but by the time we reach positive 30, the sodium is totally dissipated. It's no longer depolarizing the cell. And now all we have is potassium leaving the cell, known as potassium efflux, causing the cell to repolarize. And because those gates are so slow in closing, this cell does what's described as hyperpolarizes. That is to say, it's going below negative 70 millivolts. Why is it going below negative 70 millivolts? Well, because it can, because those potassium channels are still open and potassium is leaving, and it stops leaving at around negative 90 millivolts, even though those potassium channels are still open, or theoretically they're still open. One thing I want to point out is that there are sodium and potassium leakage channels, so potassium could be leaking out in addition to the potassium leaving via the voltage-gated channels. Why does it stop at negative 90 if those potassium channels are still open? Well, it's because potassium has reached its equilibrium potential. So even though there's still a bunch of potassium inside cells, it stops leaving the cell because it has reached its equilibrium potential. I'm not suggesting that all axons and neurons allow potassium to reach its equilibrium potential. Those voltage-gated channels may close sooner, but in the event they don't, potassium will stop leaving the cell, stop repolarizing the cell, stop hyperpolarizing the cell because it's reached its equilibrium potential. Now, one thing I want to talk about is what allows this neuron, this electrical activity, to return from negative 90 that we see here to go back up to this point of negative 70 at the resting state. So one thing I do want to say, even though we're dealing with negative numbers, negative 70 is more positive than negative 90. Now that really may not make any sense because negative 70 certainly is not positive, but it's certainly less negative. So some positive charge needs to be added to this cell to bring it from negative 90 to negative 70. So let's take a look at options of how this happens. Could it be potassium channels? Absolutely not, because potassium has reached its equilibrium potential and it's no longer going to leave the cell. And to be clear, it also wouldn't make sense because if potassium is leaving the cell down its chemical gradient, there's still a ton of potassium in these cells. When potassium leaves cells, it causes cells to become more negative, not more positive. Once again, to go from -90 to -70, that is becoming more positive. So it cannot be potassium. What about the sodium-potassium pump? The sodium-potassium pump pumps 3 sodium out of the cell in exchange for 2 potassium inside the cell. That is to say, it's going to make the cell more positive on the outside than on the inside, merely by the fact that 3 sodium are being pushed out of the cell in exchange for only 2 potassium. So it's going to be more positive out here than it is in the interior. So we're not making the interior of the cell more positive via the sodium-potassium pump. Sodium gated channels. Sodium gated channels are not an option because we already discussed that those sodium gated channels open and close very swiftly. So these sodium gated channels are closed. Now, if they were open, certainly that would cause it to go from -90 to -70 because -70 is less negative or more positive. So the only reasonable answer is the sodium leakage channels. These sodium leakage channels, which are always open, allow sodium to continue leaking out of the cell, bringing the cell back up to -70 millivolts. So in our next video, we'll talk about neurons in much more detail and how graded potentials and action potentials influence the release of neurotransmitters.